amount of the zinc is substituted by iron, so we can call the mineral as magnetite. So magnetite contains slightly more iron, which will bring more assignments for the following processes. And some very famous or very large mines all over the world, and you can see they're from Europe, from Portugal, from Sweden, from Russia, from Canada, and from Australia. And we can find reserves, so it's around several million tons. And Canada is very rich, this is more than 10 million tons. And the grade, or say the cut-off grade or the average grade of the zinc content in their reserve, so it's several grades, and the highest grade can be 16, and the yield of zinc was around 53,000 tons of zinc, and this is zinc concentrate. So this is more than 2 million tons of zinc concentrate, and the concentrate always contains around 40 to 50% of zinc. So this is around 1 million ton zinc here, and all those famous zinc reserves are sulfides. So this is why I have explained that nowadays we are using zinc, which is mainly produced from zinc sulfide. And this sulfide can be processed with flotation technique. And after that, we can get a higher zinc content concentrate, which can be used in the following flow sheet. And this is a grade of the lowest grade of their mines. The overall recovery rate of zinc in this flotation process ranged from 72% to 90% around 90%. So we are losing some 10 to 30% of zinc in this flotation process. So this is why a lot of researchers are trying to find better flotation technology, try to synthesizing new regions for the flotation, or developing new equipment in enhancing the recovery rate of zinc in this flotation technique. But we are metallurgists. We are dealing with the sulfide, which has been enriched in the concentrate. So this is the concentrate. So this is a mineral liberation analysis of the sulfurate concentrate. You can find those red particles. So they are sulfurite, and it contains more than around 70% zinc, and the rest are sulfur. But besides zinc and sulfur, we also have chalcopyrite, which is rich with copper, iron, and sulfur, and arsenopyrite, which is rich with arsenic. So you still remember I have been talking about the arsenic problem in copper making. So arsenopyrite is also available in our zinc concentrate. And also the pyrite, also calcite and condensate. So they are impurities, or they are gangue components in our zinc sulfide concentrate. And our work is mainly based on this composition, of phase composition or chemical composition. And if we go further with SEM, so we can find out that our sulfurite always contains some pyrite. So this is the pyrite, which is brighter, and this gray phase is sulfurite, zinc sulfide. So they are very well attached, and both of them are sulfide. So it's very difficult to separate them in the flotation stage. So we have to take care of that in the metallurgical process. Besides pyrite or besides iron, we also have galena, which is lead sulfide, PBS. So this is rich with lead, and the lead goes along with zinc sulfide, sulfurite. So the separation of lead and zinc should also be taken care in this flow sheet. And there are two concentrates, zinc concentrates and two lead concentrates. And let's look at the composition of zinc concentrate. This is number one, this is number two. The zinc content in the concentrate ranged from 48 to 55. So it's really rich. And if we look at the content of sulfur, this is another 30%. So the total of zinc and sulfur exceed 80. So there are very small amount of impurities or gangules which should be separated in the following technologies or following flow sheets. So this is why zinc is easy to produce, or the price of zinc is really cheap nowadays. But along with the depletion of zinc ores, the price of zinc may have some changes in the future. Besides zinc and sulfur, so we look at some other components or some other elements like copper. You still remember that I have told the cutoff grade of copper ore in China is 0.2%. And here we have 0.4% copper in zinc concentrate. So this is zinc concentrate. This is also a copper ore which can be economically processed. So copper, and we have also silver. So you can find around more than 100 grams per ton silver is available in this concentrate. So a lot of silver can be produced in the zinc and the lead processes. So besides the copper and silver, I have already mentioned that germanium, gallium, indium, those scattering elements are also available in this zinc concentrate. And the production of those scattering elements are mainly from the core products or the byproducts of zinc processing. So besides those valuable ones, we also have some toxic elements like arsenic, bismuth, and also lead and cadmium. They may have some environmental issues within or in the extraction processes. So we should take care of that as well. And also the lead content. We know that the lead content is around 1%, but when we remove or when we extract the zinc and sulfur from the concentrate, this number will be enlarged by 10 times. So it will be quite rich with lead. So we should extract the lead as well in the following process. And in the same way, so in the lead concentrate, there are around 70% of the concentrate is lead, and there are around 4% to 5% they are zinc. So same story here. So when we extract the lead from here, the zinc is also enriched. So those zinc should be also recycled or extracted. So this is why I have made a sentence here. So lead and zinc concentrate contain both of them, and the coarse melting is more reasonable. So let's make some conclusion. The assignments of zinc extraction, and now we have the idea zinc is mainly produced from zinc sulfide, and the zinc sulfide can be enriched with flotation, and the concentrate contains around 45 to 60% of zinc, so it's very rich, and the iron content is generally ranged from 5 to 15. So iron is an impurity, or is the most important impurity elements in non-ferrous metal production. So we should find a way in removing iron from the system or from the zinc concentrate. Gangue components like silica, calcium oxide, magnesium oxide, and they are gangue elements. We know that gangue components can be separated by slagging in copper making, in nickel making. But in zinc, we are using hydrometallurgy, and those components can be separated with the solid and liquor separation because they are, some of them, or their transitions phases are insoluble in aqueous solution, so they can be separated. So how to design the process, and the sulfur, arsenic, lead, cadmium, so and other elements, they are harmful, and they will have environmental issues. So this should be studied. And how should we turn the harmful into benefit? So this is an assignment we should answer. And precious metals, as I have already explained, the silver is popular in the zinc concentrate around 100 gram per ton, and it can be 1000 gram per ton in the lead sulfide. So this is why we are also put this precious metal recovery as an assignment in zinc extraction. And also platinum group metals and some scattering metals like germanium, India. So they should also be recycled. So integrated recovery is needed in zinc extraction. And I have some example today to tell how to simultaneously recover those elements in one flow sheet. And the last assignment in my mind or in our discussion will be there are some energy. You know that the energy in the concentrate can help the process, and in copper making, actually, it can be energy free in the pyro units. But here in zinc production, zinc sulfide is processed as in the first stage. And how about the energy? Is there any solution of recovering the energy? And the majority of the zinc nowadays in application or in use are produced with this technology. So the roasting, leaching, ion removal, solution purification, electrical weaning. So this is a traditional and very popularly used technology. But before we cut into the details of the technology, and we should have the summary, the bird view of how refined zinc is produced all over the world. And the number in our accounting is that primary zinc accounts for 96%. So very small amount of zinc is recycled nowadays, but this number is increasing, and this is a tendency in the future. So this number will decrease, and this number will increase. But nowadays, the primary zinc making is still dominant. In the primary zinc producing, the leaching electric deposition, so the technology here, roasting, leaching, ion removal, purification, electrical weaning. So this is the dominant, so accounts for 85%. So this is the main technology. So this is why we are studying it today. And the pyrometallurgy can also be used like Empire smelting process, which is developed in England around 100 years ago. So it can process lead and zinc concentrate simultaneously. So this is, I would like to say this is the genius work, but the zinc produced with this pyrometallurgical technologies are very small, are very limited. And in the secondary zinc production, so both hydro and pyro can be used. And in secondary zinc mainly stays with oxide form or metallic form. So hydrometallurgical method is more suitable here. So let's have the conclusion. So leaching, electrical deposition, electrical weaning. So this is a dominant technology. So we are covering it one by one. So first of all, so this is how zinc is produced with this hydrometallurgical process. But we know that the first roasting, so roasting is a pyro unit, so which is used to help or to assist the following treatment of the alkaline. And this flow sheet is a combined one, and we can cut from here, and on this side, so this is a traditional, so contains roasting, the neutral leaching, hot acid leaching, and super hot acid leaching, and the ion purification, and the liquor is returned for nature leaching, and the solution phase in the natural leaching is sent for purification and electrical cleaning. So this is a flow sheet. We are using the roasting, leaching, iron removal, purification, and electrical cleaning. So this is the full flow sheet of zinc making. And on the other side, on the right-hand side, we can find the concentrate, which is zinc sulfide, can be directly used as a raw material. So pressure leaching is also available. Next, the oxygen pressure leaching developed by Columbia, and also the atmospheric leaching by Artec. They can directly used in treating the zinc sulfide with the help of spent electrolyte. So it can be, we can recover the zinc in this routine as well. But this is the application of this technology is limited in the world, and this is dominant one. So we are mainly focusing on this part. So first of all, let's go to the roasting. The roasting. So how to conduct a zinc sulfide mineral roasting? Actually, I would like to start, or I would like to explain with the same strategy of this course. So first of all, we should think, or we should study it thermodynamically. We should know how zinc sulfide can be treated, or how it converts in the process. So we start with zinc sulfide, and we need to remove the sulfur from the sulfide, or from the concentrate. So oxygen will be used. And we should draw the ternary diagram of zinc, sulfur, and oxygen. So there are some steps of determining the stable phases in the system. So zinc, sulfide, sulfate, also some compound, also some gases. So the reactions can be written, and we can find the thermodynamic data. And we can find the relationship and combine them into a chemical potential diagram. And we can check it. And here we have it. So this is a very old picture I found from the textbook. So the x-axis is oxygen partial pressure, and the y-axis is the sulfur dioxide partial pressure. And we have three temperatures. This is 600 Kelvin, and 1100 Kelvin, and 1200 Kelvin. And this is very close to the industrial temperature of the roasting. We can find, so look at the picture at the 1100 degrees C. So zinc sulfide, this is the main phase in zinc concentrate. So we start from here. So once we are increasing the oxygen partial pressure by roasting, so we are supplying oxygen into the system. So this one will be oxidized. So we are getting zinc oxide. So sulfur can be efficiently removed. But along with increasing of the oxygen partial pressure, the zinc oxide will transfer to the alkaline sulfate, even zinc sulfate. And this is how to say, there should be a discussion. So if we can convert zinc sulfide into zinc sulfate, so this is durable. And zinc sulfate can be directly leached with water. And after that, electrical cleaning can be used in recovering the zinc. And probably you have the question, if we can start from roasting and get the zinc by electrical cleaning, while we are doing the flow sheet in such a long steps, such a long flow sheet. And the problem is that if we are producing zinc sulfate in the roasting stage, and this can be leached with water, but in the electrical cleaning part, the sulfate will convert to sulfuric acid. So the amount of acid in the system will accelerate. So there we should find a way, or find a routine for the utilization of sulfur. So if we are converting zinc sulfide into zinc oxide, the sulfur enters the gas phase. as sulfur dioxide. And sulfur dioxide can be easily used in making sulfuric acid. So it can be well recycled. And this one can be used as a material, the cation can be used for lynching, and it can be further recycled with electrical weighing. And the metal balance and acid balance can be obtained simultaneously in this routine. But if because of the loss of some acid in practice, there are always some small amount of zinc oxide, zinc sulfate, this kind of compound in the roasting stage, in the product, to add or to supply some sulfate ions into the system to get the acid balance recover it. So when we are increasing the temperature from 600 to 1200, we can find out that the area of zinc oxide increased. And at higher temperature, we have better kinetic conditions. We are usually doing that, like that. And point B and A are the points we are doing in industry nowadays. So as you can see, so this is a work made by HSC 5. So this is 914 degrees C. Actually, this is from a thesis from Oulu University at 2004. And this is a gas phase composition, so around 10% sulfur dioxide and 5% oxygen. And this is a place or area processing window of the roasting. So zinc is mainly produced, or zinc mainly converted to zinc oxide in the roasting process. But I have already mentioned in the introduction part, besides zinc, there are lead, copper, and silica, iron in the system. So the behavior of the other elements will also influence the following processing units. So we should know the behavior of other elements. So this is the processing window of zinc, but the behavior of impurities should also be paid attention to. So first one is copper, and we know that in the ore dressing process, copper are staying with copper sulfide form, so it's chalcopyrite or some other form. And in the processing window of zinc sulfide roasting, so we can find out that copper will convert to cuprite or tellurite, or copper or Cu2O or CuO, but it doesn't matter. So these two can be lynched, and they will enter the solution. So we know that in this roasting window, so copper will convert to copper oxide. And this is mainly determined with the temperature. So at lower temperature, we have CuO, and at higher temperature, we have Cu2O, because copper monoxide is stable at higher temperature. And also, along with increasing oxygen partial pressure, we will have copper oxide in +2 oxidation state. And the behavior of lead can be explained with this two figure. And we can find in the processing window of zinc roasting. So the lead will convert, or the lead will stay in the form of lead sulfate. And it starts from lead sulfide and ended up with lead sulfate. In the lynching stage, we are using sulfuric acid, and all of us know that lead sulfate is insoluble in sulfuric acid solution system. So this one will terminate into the lynching residue. And also, along with increasing the partial pressure or varying the oxygen partial pressure, or the temperature, so the lead always stay with lead sulfate. And this is a picture of the real actual particles, zinc sulfate particles after the roasting. We can find out that this is a layer made by lead sulfate. So this is a particle. So we know that during the roasting process, the lead is moving towards the surface and forming this lead-rich layer and warps the particles. But this layer may have some harmful effects in the leaching result because it hinders the penetration or the transferring of the aqueous solution into the particles. And in the middle of the particle, we can find this is rich with copper. So copper will migrate into the core part of the particles. So we know that. So if there are some copper remaining, so it will stay with sulfide, and also it will stay in the particle core part, or in the particle center. And the contents of lead, copper, and silica in the zinc concentrate has a standard, and the total should not exceed 5%. And this is mainly because or determined by the behavior of those systems. In the roasting part, if we have too much lead or too much silica, we can find out that. So very large amount of liquid. So this is fully liquid phase area. So around 714 degrees C, lead oxide and silica can form a liquid phase. And also the lead oxide can form a liquid phase with ferric iron oxide. So it's around 752. And also the copper oxide and lead, so it's below than 700. And all of us know that the roasting is carried out at 940 degrees C, 20 degrees or 50 degrees C lower or higher. And this is much higher than the liquidus temperature in those systems. So if there are a lot of lead, copper, or silica in the concentrate, the roasting process cannot be carried out because all those particles will be covered with this liquid phase. And the transportation of oxygen into the particle and the transferring of sulfur dioxide to the ambient atmosphere will be hindered by the liquid layer. So the amount of these three impurity elements should not exceed 5%. So this is also should be emphasized. And besides the impurity elements like lead, copper, and silica, and another very important impurity element is iron. And I have the idea, or I have talked with a lot of people and said that iron is the main target which should be removed in non-ferrous metallurgy, no matter what kind of metals you are dealing with. In copper, so we should remove the iron by slagging. And in zinc, we should remove the iron by the iron residue or by some other form. But in the roasting part, how iron behaves is also under our consideration. And this is a predominant phase diagram of iron and zinc oxide. So in this temperature window, we can find out, in this processing window, we can find out that zinc stays with zinc oxide, and iron will stay with ferric iron oxide form. And this is acidic oxide, and this is basic oxide. And these two can form a compound. We call it zinc ferrite. And this is a headache for us, especially in zinc metallurgy. And there are a lot of references you can find from MMTB, from JM. They are talking about the formation of zinc ferrite in the roasting part, in the roasting unit of zinc production. And also they are telling us how to dealing with zinc ferrite. And the roasting is carried out in a fluid furnace, the Lucci roaster. And this is the size of 123 square meter. Tells about the size of the Lucci roaster. And nowadays, the largest one is 158 square meter, which is built in Shuikoushan in Hunan province, which is around 200 kilometers from our campus, which is the largest one. And 123 square meter can produce the zinc taconite for around 100,000 refined zinc production in one line or in one factory, in one plant. And 158 square meter Lucci roaster can supply the taconite for the 150,000 tons of refined zinc production. And this is some very well-developed, very well-studied numbers, just like the height of the diameter, and they are well-designed. And some examples of the parameters of Lucci furnace all over the world, like Risto, Kukla, and even some companies in Japan. So the square meter of the bed, the 128 used to be the largest one in the world. And if we are looking at the bed areas, the size of square of bed area, so it's 120, 72, 32, and 48. And if we are using larger ones, we can actually, this one can produce a similar amount of 4 small Lucci roaster of 48 square meter bed area. The processing temperature in different company, they have different process temperature. It's mainly determined by their zinc concentrate, the quality, and also the content of those impurities. Some are lower and some are higher. And this is around 1020 degrees C, and this is lowest one is around 930 degrees C. So it's around 940 degrees C all over the world. And we can get very well enriched sulfur dioxide. Let's say this is a concentration of sulfur dioxide of gas. This is around 10%. And all of us know that if the sulfur dioxide concentration is more than 4% of gas, it can be very economically used in making sulfuric acid. So this is how sulfur is recycled or recovered in zinc production. And in the product of the roaster, so this is the taconite. So we can find the zinc content is around 54 to 60. So we can find out that the sulfur is replaced by oxygen, and the concentration of zinc slightly increased. And the iron stays here, but the total amount of sulfur decreased very much. And the sulfur stays in 2 different forms. So some of them are still as sulfide forms, like zinc sulfide, which react into the core part of the particles, which didn't react with the oxygen, and it was still zinc sulfide. And also there are some copper sulfide, which migrate into the core and also stays in the taconite. And also the sulfate is mainly contributed by the lead sulfate as the coating layer or the outside layer of the taconite. So this is the picture. So this is as in photograph of a partially roasted. So this is not fully made, but we can find how iron is moving in this process process. So this is rich with iron. So iron is also rich in the coating layer or in the layer part, and this is the shuriken part. So this is also rich with zinc and iron. So this is sulfide, and this is oxide. And once we convert the sulfide into oxide, they are becoming porous. So which is very good or beneficial in the following leaching part. Our sulfuric acid can react with our cacnine very well with good connections. Okay, so this is the roasting part. We got to the conclusion. The zinc sulfide will convert to zinc oxide, mainly convert to zinc oxide, and some of them will stay with zinc sulfide. And the other impurities like lead, they are converted into lead sulfate. Iron, they will make zinc ferrate, which is a headache in the following part. And the copper will stay in the copper oxide, which can be easily processed. And in the leaching part, we are actually in the roasting part, sulfur is separated and recycled in the following acid-making process. And in the leaching part, we are separating the gangules and even some impurity elements. For example, here we can find the zinc oxide, which is a dominant phase in the cacnine or in the roasting product. So this is here. So once we are decreasing the pH value of the solution, zinc oxide converts to zinc ions cations in the aqueous solution. So which can be further recovered by electrical veining. Some other gangue parts like alumina, like magnesium, like calcium oxide, they will also convert to cations. They can be leached out. But some others, like if we are looking at iron oxide, especially ferric iron oxide, we can find out that it needs not a very strong acid in transferring ferric iron oxide into ferric iron ions in the solution. So if we are controlling the pH value of the system in this part, so our zinc will convert to zinc ions, but ferric iron oxide will stay as oxide. So they will enter the Lynch residue, but zinc will report it to the aqueous solution, which is benefit for the following recovery. And also, if some of them are leached out, and the cations may have hydrolytic precipitation, we can find, so this is the zinc, so this is the target, So the copper can precipitate before zinc, so it can be also enriched in the residue, and lead as well, and tin, iron, so they can be collected in the Lynch residue. But the others, like cadmium, magnesium, or calcium, they will stay as stable cations in the solution. And in this picture, we should pay attention to the difference between this one. So this is the ferrous iron oxide, and this is the ferric iron oxide. So there are huge difference between the pH value or the endpoint of the precipitation. So this need actually at very strong acid conditions, ferric iron will precipitate, but ferrous iron oxide will not precipitate in this range. So once we are crossing pH value of 7, so it starts to precipitate. So we have the idea that iron should stay as ferric state or trivalent oxide state, and it will benefit in the separation part. So we are using some oxidation reagent in the lynching part to oxidize iron to ferric and get it precipitated in the slurry. And the pH value. So besides the pH value, the potential is also another important process diameter we should pay attention to. So this is zinc hydroxide, and this is the stable region for zinc ions, cations. And this is hydrogen evolution, and this is oxygen evolution. So in this part, so it's very wide range. So zinc can stay very stable in the aqueous solution at very, how to say, very fine or very gentle requirements of the solution. And if we have some zinc sulfide in the solution, so it can also convert with the reaction 1 with some oxidation, and we can get some zinc ions. We can get sulfuric ion, or with reaction 6, we are getting the zinc ions. We can also get some sulfate ions. And this is also used in the direct lynching with this reaction 1 in the Autotech atmospheric pressure lynching, and also the oxygen pressure lynching developed by the Canada companies. So we have grouped those elements in the Cas9 into 3 groups. So first group is lead, calcium, magnesium. So all of them are insoluble with their sulfate form. So majority of them are entered into the slurry as sulfate. And also silver goes along with lead. So we call it lead and silver slurry, especially after acid lynching. And calcium and magnesium partially dissolved into the solution, and which is negative. So you can see there are pipes in the practice. So they will precipitate on the surface of the inner surface. So this will reduce the capability, or reduce the volume, the available volume of this pipe. So along with the time, so this will influence the process. And some studies has provide information about the solubility. So the temperature make influence with the solubility of calcium gypsum in the solution. So by verifying the temperature, we can get it precipitate. So this is how gypsum can be removed or separated. And when treating high magnesium zinc concentrate, this one can be as much as 15 to 30 grams per liter. And this should be removed, otherwise it will influence the electrowinning process, also the transportation of liquid solution. So the magnesium was reduced by Pig9 zinc concentrate or discharge method after neutralizing zinc in the waste electrolyte. So magnesium is removed. So this is the first group of lead, magnesium, and calcium. And the second groups of elements are zinc, copper, cadmium, nickel, cobalt. And we have the knowledge that all of them are target valuable elements. We should recycle them. So, and those metal elements are soluble in their sulfate form, and they have very high solubility. Especially, we can monitor it by varying the pH value of the system. So medium immersed suspended composition, so we can find the zinc concentration can be as much as 170 grams per liter, and the others we can have some amount of copper and some amount of cobalt, nickel, and also germanium. So they are valuable ones. So we should recycle them. And they are recycled, especially the copper, cadmium, antimony, nickel, cobalt, and the germanium. They are enriched in the purification part. And the last part are toxic ones or impurities like iron, arsenic, antimony, germanium. So this is a good one, and we should recycle them. And a lot of studies have been made in Finland, in China, and in companies. And this is, how to say, a strategy elements, strategy metal in the future in military, in daily life. And those elements were hydrolyzed into media lynching slurry. So they will enrich in the lynching residue. And also, I have already told, ferrous iron should be oxidized to ferric iron in the lynching process in order to get this one precipitated in the hydroxide form. And ferric iron hydrolysis in the form of ferrohydrate. So the pH value of 5.2, this is isoelectric point. So this precipitate do not have any electrical performance. So it was totally inert. So it will precipitate, it will colloid, it will precipitate fast, rapid, and big particle size. And along with the precipitation of ferrohydrate, the other impurities like arsenic, antimony, so they will co-precipitate, especially when the mole ratio between the atoms like iron and antimony, arsenic larger than 10. So they will co-precipitate. So we know that with the lynching slurry, we can enrich arsenic, antimony, also germanium. So it will colloid and also precipitate as well. Silica, so it will polymerize into this one and colloid and reported to the lynching slurry. But this one influences the separation of the solid and liquid. So three groups have been made in telling the behaviors of those elements in the lynching part. And there are different technologies in the lynching stage. And the natural lynching, so this is available all over the world in the zinc plant. And the final pH value of natural lynching is 5.2. As I have mentioned, this is determined by the purification of iron hydroxide, and temperature is 50 to 60 degrees C, and it has two effects. The first one is lynching. So the zinc will report the zinc, nickel, copper, cobalt, those valuable elements, they are lynched out and enter the solution phase. And the other impurities will precipitate along with iron. So purification effect also used here. And we are always using some oxidation reagent like magnesium oxide in oxidizing ferrous iron to ferric iron in order to get ferrohydrate. And the mole ratio of those impurities are well monitored to ensure the co-precipitation. And the germanium and silica is also enriched and was enriched as in the slurries. Okay, so we know the behavior of different elements in the lateral lynching stage, and look at the mineral composition of the low acid lynching of natural lynching. We can find out that the total zinc concentration in the lynching slurry is around 20% or more than 20%. So this is not acceptable. So only 80% is lynched out in low acid lynching or natural lynching. And around 20% still remains in the lynching slurry. So we should find solution in recovering them. But before we find solutions, we should figure out why they are not lynched out. And the mineral analysis are presented in this table. We can find here, majority of the zinc stays as zinc ferrite. as we discussed in the roasting stage. So this one form in the roasting stage, and it cannot be lynched out in the natural lynching stage. So it will enter the slurry phase and get enriched. Small amount of sulfide is still present here, but this one is a minor part. Some silicate formed and some oxide formed. And this one is also actually mainly result from the washing unit. So if we are washing it by 2 or 3 times more, this one can be recycled. And this is a major part, and this is the problem we should figure out. And a lot of reference have been made in figuring or in finding solutions in getting this zinc recovered. And this is a phase diagram of the zinc iron hydrogen system. This is a two systems. So zinc, water, iron, water. So this is the two system and combined here. So this is a zinc ferrite, and this is a solid line, is 25 degrees C, and the dust line. So this is 100 degrees C. We can find out that. So when we are decreasing the temperature, the stable zone of zinc ferrite or reduced. And if we want to actually, this is contradictory with the lynching requirement. The zinc ferrite stable zone expands when we are increasing temperature, and low temperature is favorable to lynching the zinc ferrite. But this is thermodynamically. If we are doing the zinc ferrite lynching in industry, high temperature will be required because of kinetic requirements. But thermodynamic analysis told us that the lynching of zinc ferrite is an external process. So in order to get the zinc in the zinc ferrite recovered, acid lynching is developed. So in acid lynching, the terminal acidity is 1 to 5 gram sulfuric acid in the solution. So if you convert to pH value, it's around 1 to 2 terminate pH value, and temperature has been increased. The natural lynching is 50 to 60, but here is 10 to 20 degrees higher than that in order to get the zinc ferrite lynched out. So after washing and lynching, so it was further treated. So after 2 stages of lynching, the lynching rate of the zinc was about 85%. So previously, it was lower than 80%. After acid lynching, it can be improved with 5%, and the lynching slurry was around 50%. And there are still 20% of zinc, 10% of zinc. So we should get better performance. So some new technologies have been developed in first stage, hot acid lynching. So the temperature was even higher, almost reaching the boiling point of ambient solution. The terminal acidity is 20 to 60 gram of sulfuric acid. So there is a very strong acid and very high temperature. So the lynching residue can very well dissolve zinc ferrite. But when we are lynching zinc ferrite, zinc enters the solution, so does iron. So the solution contains more than 30 gram per liter of iron, so which should be removed. The specific methodology should be developed in removing the iron from the zinc sulfate and sulfuric acid solution system. So a lot of technologies like jarosite process, geosite process, or hematite process. So this is why we are going to the iron removal stage. So let's make a let's look back at our lynching stage. After the roasting, we have calcinine, and the zinc stays with zinc oxide, and some amount of them are still as zinc ferrite. And in the natural lynching stage, zinc ferrite is not lynched. So in order to recover zinc here, so the acid lynching and hot acid lynching are developed. But when we are lynching zinc, the iron enters the solution as well. So we have to find technologies in removing the iron from the solution. And besides the hot acid lynching, there's another technology which can efficiently treating the zinc ferrite. So it's sulfur dioxide reductive lynching. So this is the Corey reactions. So this is zinc ferrite. So with reducing by sulfur dioxide in the acid solution. So this one goes to ferrous iron oxide, and zinc is lynched out. So in this part, we are getting the zinc sulfate solution, also ferrous iron oxide solution, and which can be used in the following precipitation part. So this is a very well designed and developed technology. So in the lynching part, two major equipments are used. First one is the lynching tank. So with an agitator, and even sometimes we are pumping some gases. As I have mentioned, some oxidation reagent should be supplied to transfer the ferrous iron into ferric iron to get the core precipitation. And once we get this lynched out, and the solution and the slurry, the mixture, were transferred to the thickener, and the solid particles colloid and precipitate in this part and settle down and settle on the surface of the thickener. And this rate slowly moves and get those solid particles enriched in this hole and get it connected. And the overflow of the solution can get further treated, sent to the purification and electrical cleaning, or returned for the natural lynching. So this is equipment for lynching. The zinc lynching and iron removal with zero-sand methodology, as I have already mentioned. So we are going to this is concentrate, start with concentrate. So roasting, we get calcinine. The calcinine was sent for the natural lynching. And after the natural lynching, the purification stage is here. And the purified solution can be sent for the production of zinc, a cathode zinc. And the lynching residue is sent for the weak acid lynching. And the lynching slurry is further sent for the pressure or the further lynching of the pressure acid lynching, or the hot acid lynching, or strong hot acid lynching. So in order to get the zinc recovered. And some solution phase, are recycled or returned for the precipitation part, for the jarosite precipitation. And we can get a jarosite, which is iron mineral. So iron is separated in the form of jarosite, and zinc is recovered with cathode iron, and the sulfur is recycled as sulfuric acid. So there are three major elements in zinc production. And some other elements like copper can be recycled in the purification stage. So this is a full flow sheet containing the lynching, the roasting, lynching, purification, iron removal, and electrical cleaning. But if we are lynching the zinc ferrite into the solution, and we have to remove the iron from the solution, and the solution is a system containing ferric sulfate, sulfate acid, and the zinc sulfate. They are major components in the system. And how can we get iron removed? So we learn from the nature. What kind of minerals can be synthesized in this system? And this is a phase diagram in this system. So this is a amount or weight percentage of ferric iron in the system. So this is very small numbers. And this is the temperature. And below 100 degrees C, we can process at ambient atmosphere. But when we are going above 100 degrees C, autoclaves are needed. And this part is the sulfate acid percentage or sulfate acid content in the solution. And here we can find hematite. As I have mentioned, we are learning from nature. So hematite is popular in the nature, and it can be synthesized in this system. And we know that if we are aiming at hematite, so we should have very low content of ferric iron. So this is not acceptable. So this one should be reduced to ferrous iron. So ferric iron is not acceptable. And also, if we are aiming at hematite, the acidity should be controlled. So if the pH value is too low or the acid is too much in the system, the hematite will be lynched out or will dissolve again. So we should control the sulfate acid content in the solution, so it should be neutralized. And if we are aiming at hematite, the temperature should be above 100 degrees C. So autoclaves are needed. So if we are aiming at hematite, so low ferric iron content, low sulfate acid, and high temperature are needed. And geosite is also popular in the world or in the nature, but it can be processed or synthesized at atmosphere at below 100 degrees C or at atmospheric conditions. And also, very small amount of ferric should be available in the system, and also the sulfate acid concentration should be controlled. And in the middle, we can also get jarosite or another form of iron minerals. So this can be synthesized around or approaching very close to the boiling point of the system. And the sulfate acid concentration was relatively higher than the other two, and also, but the ferric iron concentration should be low. So the conclusion is that, so this is also thermodynamic analysis. So ferric iron concentration should be controlled. Acidity, temperature should be monitored. And this is minor, or this is easier to control. So this is more widely used. And geosite and hematite are used, but they need higher cost and better controlling. And this table summarized the process of hematite, geosite, and germicide. We can find they are iron minerals. They are chemical formulas. We can find this is iron oxide, contains around 70% of iron. So this is probably can be used as a raw material for iron making. So does this one, so contains around 70. And this jarosite contains around 30%. So this is a waste, is a solid waste. And also it contains sulfur, contains acid, contains zinc, and contains iron. So all of them are produced in hydrometallurgical processes. They are porous, they contain acid, they have heavy metals. So all of them are toxic solid waste. We should find solution for them. And the amount around 220 ton hematite residue is produced when we are producing 1 ton zinc. and the ratio is 1 when we are producing jarosite. And geosite is 0.6, the ratio. So among these three minerals, this one is more ideal. We are producing more iron content residue, and the amount of the iron residue is smaller. So we are emphasizing the one here, but this is more popularly used nowadays. And the methodology or the mechanism of the iron removal, if we are using the jarosite, actually this is a picture photoed by myself, and this is actually more than 10 years ago. Actually, it's around 14 years ago, and 2007, and this is a picture by myself, and we do the experiment in our lab. So this is very well prepared jarosite, very big in the particle size, and very fast in the separation stage. And the secondary cations can be potassium, the sodium, even some other cations like even this one can be used as the secondary cations. The temperature is approaching the boiling point, and the pH value is 1.5. And also, generally, we should have some crystal Cs. So this is popularly used all over the world. And geosite has two, when we are using geosite process, there are two methods. First one is VM, we call it wheat mountain. I think this is from Middle Europe, from Belgium or somewhere. As we have mentioned, the concentration of ferric iron in the solution should be monitored. The acidity of the solution should be monitored, and also the temperature. So first step, these ferric ions are reduced into ferrous iron by zinc sulfate. So we can find out that. So the concentrate can be used as a reducing reagent. So the ferric transferred to iron. Actually, this is also a core reaction in the oxygen direct lynching. In the second stage, the ferrous iron is oxidized by oxygen and precipitated simultaneously at the pH value of 3 to 3.5 and the temperature at 80 to 90. So the oxidation speed and precipitation speed are equal to each other, and there is no accumulation of ferrous iron in the system. So this is the VM process of geosite precipitation. And another one is EZ process. So the temperature is similar and pH value are similar, but the strategy is different. They are adding the ferric iron into the reactor in slow speed, and the precipitation speed of ferric iron equals to the adding speed. So this is very well designed and saves one, actually cut one reducing reactor. And this is a picture of the geosite. We can find out that they are porous, or they have very big specific surface area, and they will take away more sulfuric acid and zinc sulfate. And the precipitation is a mixture of several iron minerals. And the last one is hematite. The hematite, we can find ferrous iron is needed. It was oxidized and also oxidized, and after that it was converted to hematite in autoclaves. So the middle lynching residue was reduced and lynched by high pressure sulfur dioxide lynching. Actually, the lynching reagent is sulfuric acid, and the pH value was 4. And in an autoclave around 200 degrees C, we processing with 3 hours, and we are getting this hematite because of the application, because of the utilizing of autoclaves and the long processing residence time. So this hematite process needs more energy and needs more cost. So it's less used in industry. industry. But it's very well designed because it has advantages in recovering several valuable elements. As we can see, if we are using hematite, so the concentrate after roasting and hot acid lynching reduction nutrition. So we can find the calcination also sent here for the neutralization, and after hot acid lynching, the ferric iron concentration reaches 30 gram per liter. So we are using some concentrate for reduction. So ferric iron are reduced to ferrous iron. And further, we are using some calcination to get the pH value of 4. And we are preparing the hematite in autoclave and iron enriched or was separated in the form of hematite. And after hot acid lynching, lead and silver are very well enriched, and we are getting silver and lead concentrate or slurry. This can be separated, individually processed, and silver can be very well recycled. And the lynching solution of the natural lynching, after purification, you can get in copper and cadmium cake, and this can be used for the copper recovery and cadmium recovery. And after that, we are using electrical veining. So this is a hematite method. And this is, I think, one of the most advanced zinc hydrometallurgy process in the world. So this is Akita zinc in Ijima plant. We can find the natural lynching with acid lynching. So we are using sulfur dioxide autoclave lynching. So here we are producing one residue which is rich with silver and lead. And after that, first neutralization, we are using calcium carbonate. So we are producing a gypsum which can be used as a byproduct, sort of the byproduct. And second, we are using calcium carbonate as well. And here we are recycling the germanium and gallium and indium in the system. In the system. And after that, we are using the hematite process in preparing the hematite precipitate. And lastly, the copper can be recycled in the purification stage. So this is a connection of their equipment. So autoclaves are used in the sulfur dioxide reducing lynching and also the hematite precipitation. The di-iron solution can be used for the purification and electrical veining. And here we are going to the purification. And in hematite, we can find the gas, the cyanotic content of iron is 70%, but in industry it's around 54% to 60%. So this is quite high, and which can fit the standards of iron oxide concentrate, iron ore. And in hematite precipitation process, the residue or the slurry is also a mixture of several different kinds of iron minerals. So contains of hematite, some jarosite, and also some soluble sulfates. And along with increase in temperature, and their crystal structure can be improved. So this is the iron removal. So after iron removal, the pH value is around 4 or slightly larger than 4, and they are ready for the purification. So after iron removal, we can find the solution contains quite a large amount of zinc, and iron content can be very well controlled. But here are some other numbers, like copper content, cadmium, nickel, cobalt, antimony. And this should be recycled, and this is the first target. And second, those elements have negative impacts on the electrical veining. So we have to remove them in the purification stage. Otherwise, we are losing those valuable metals. Simultaneously, we are we are, how to say, postponing the problems in the electrical weaning process. So we should solve those purification problems in this part. And copper, cadmium, nickel, cobalt was removed from the linear solution to meet the electrical weaning requirements, and also the recovery of those elements can be achieved here. So you see, if we are not doing the work well, we are getting unqualified zinc cathode. And if we are making some SEM pictures, you can find some pores and some nut crystals on surface. And they contains copper, cadmium, nickel, and they cannot be sold directly, and we are losing those valuable metals. And the mechanism is we are using zinc powder in replacing them. So zinc powder are used in substituting those ions in the solution, and we are producing those residues as cakes. And we are not going to discuss those problems. And because of the overpotential of the oxygen forming, and also the overpotential of precipitation on different metals. So zinc will firstly precipitate in the cathode, and in the anode, we are getting oxygen, And how to do the purification? So ASIC assisted purification method. So the first stage, or the first one, cobalt, nickel, and copper were removed when we are adding this oxide, arsenic oxide, trioxide, and zinc powder in the system. This is high temperature. We are removing copper, nickel, and copper. And the second stage, we are adding zinc powder and some copper from copper sulfate, and to remove cadmium. So first, we are removing cobalt, nickel, and copper. And the second stage, we are removing the cadmium at lower temperature. But as I have already talked in my first course, this one is toxic. In this process, the formation of this one is unavoidable. So we should have some sensors in detecting those toxic gases. This hydrogen arsenide. And arsenic can form intermetallic compounds which can lower down the potential and help this purification of those elements. So this is the first method. Second, actually, when we are applying this one, so we can find, okay, in the solutions enter the first reactor, and zinc powder is added, and we are getting the copper cake. And in the second reactor, we are adding zinc powder and arsenic trioxide simultaneously, and we are getting the nickel cobalt cake. And last one, at low temperature, like 65, we are getting some cadmium cake. So here are the place where we can recover our copper, cobalt, nickel, and cadmium. And another technology is antimony assisted. This is more widely used because it's safer. In the first stage, is low temperature. So this one, we are removing the copper and cadmium. In the second stage, so they are added and at high temperature. So they can be removed. Cobalt and nickel can be removed. So there are two technologies, but the arsenic assisted technology can get the solution purified at a lower level, and it fits the electrical weaning better. And besides cobalt, nickel, copper, and cadmium, there are some other impurity elements, like halogen elements. Halogen elements can be removed beforehand, just like in the roasting part, majority of the halogen elements will report to the gas phase and can be removed. But along with the increasing of halogen-containing materials in zinc production, the contents of halogens like chloride or fluorine in the solution are increasing. So we have to taking care of that. So cuprous oxide precipitation method is used in removing them from the solution. And lastly, we get the solution purified, and lastly, we are going to the electric weaning, and the work is very simple. And one cell is built, and we are using alumina as a cathode, and we are using lead silver as the anode, and we are producing oxygen here, and we are producing zinc cathode here, and the anode always contains 0.75 and 1% silver, and this one is optimized in different universities, and a lot of people are doing work here. And the electrolyte is composite of zinc sulfate acid, and also this magnesium sulfate, also a lot of sulfate acid. In the anodic reaction, so we are producing this oxygen. Simultaneously, when we have some lead in the system, especially from the anode, it will be oxidized. And this lead oxide can protect the anode from further corrosion. And anode slime is formed, and is mainly composite of this one, magnesium oxide. And the cathode reaction, we are producing this one, the zinc precipitate, and the secondary reactions also happen, especially when we have high cobalt and cadmium content in the solution. If those impurity elements precipitated in the cathode, hydrogen may form as well. And there are some analysis I'm not going to, many vector field calculations. So the cobalt and the nickel, so the reduction potential is very positive. So the superpotential of hydrogen of evolution is small, so the causing the block solution and also thermal burning plate. Those elements, germanium, arsenic, antimony, so they have very reducing potential and precipitate into the cathode, and they are forming these gases. These gases will decompose and form those ions in the solution again, and the ions will precipitate again in the cathode. So just make a circle. So this will lowering down the electrical efficiency. And the copper, it will precipitate, and so does the others. And this is elements we should add into the system to protect the anode. And those halogen elements should be removed in deep level. Otherwise, it will lower down the lifetime of the anodes, and also does the cathodes, because it was made by aluminum. And some processing parameters: current density 500 ampere per square meter, the temperature 35, and approximately 3,000 kWh per ton zinc is needed, and it has very high purity. But the current efficiency is only 92, and there are side effects on the cathode and anode, and also some voltage decrease in the solution, and also the conductivity. And they are equipments for the electrical weaning. So this is the electrical weaning tank. So it can be made by some polymers, and they are manufactured directly, and smelters can buy directly from manufacturers and assemble them in the lines, and get those. This is an anode, and this is cathode. This is aluminum made, and this is lead and silver made, and they can be good and well organized, and we can get our zinc from the solution. Okay, so this is the flow sheet of how zinc is produced with traditional flow sheet. And I have some thinkings of the opportunities and challenges of zinc making. So first one is about complex and secondaries, such as complex ores. We know the ores may contain zinc, it contains lead and copper, also silica. So once those impurity elements are increasing, how can we process that? Whether the traditional technology is still suitable, or we should find other technologies. So this is one we should think about. And the second one, electric arc furnace, which is mainly producing zinc oxide containing dust. And the amount of the EAF dust will increase for sure. And how should we process them? And they are always rich with halogen elements. So we should find some technologies in removing halogen elements from the solution. Do we have the technology stored? And bottom ash, many sample waste, they are burnt, and the bottom ash is rich with zinc, lead, and some other valuable metals. Shall we find technologies, or how can we get or recover metals from here? This is also the opportunities. And new processes are to design, such as this ideal circulation of materials. So the concentrates or some secondaries, we are reporting or we are delivering the lead-rich residues to the lead process, and the copper-rich ones can go to the copper process. So very well recycled, and we can get as many kinds of elements recycled, and as much as metals and elements recovered. Okay, so this is I have, and thank you very much for the participants and the professors, the organizers, and our students. Thank you very much, and also my sponsors during our research and teaching activities. Thank you very much, and I'm happy to answer your questions. Okay.
Okay, Longgong. Now it's time for question, everybody.
Yes.
So get ready. Okay. Now is first question. Please mention your name and your origin. Okay. Don't be shy. Normally, first question is hard to do, but after that, oh, unstoppable. Okay, everyone.
Okay. Maximum.
Okay. Yes.
I want to ask a question, Mas.
What's your name and from where?
Okay, thank you. Let me introduce myself. My name is Saiful Rifai. I'm from ITB, and we know that there are some parameters in roasting and leaching process, such as temperature, concentrate, partial pressure, and many others. And my question is, what are the important parameters we must control in roasting and leaching, and how to control doses? Thank you.
Okay, thank you for the question. Actually, when we are doing hydrometallurgy, and zinc is a typical metal which is produced by hydrometallurgy. When dealing with leaching, actually, the system design is the most important. What kind of leaching reagent you are using, and here in zinc production, we are using sulfuric acid. And those parameters including temperature, liquid to solid ratio, and they are very important. Temperature and liquid solid and being optimized from the industry, and also we can have those optimized parameters in the lab, and we can enlarge it in the pilot scale, and after that we can apply them into practice. So the leaching system, temperature, liquid to solid ratio.
Okay, is it answer your question, Saiful? it is one of them is temperature, also the ratio between solid and liquid. So we have to control that.
And potential is another important one.
Yeah,
Just like
potential.
the Ikeda system, they are using sulfur dioxide as a reductant and very efficiently in lynching zinc ferrite from the residue. So this is very good work.
Okay, guys, next question. Yes, next question, please. We still have like 10 minutes to go, so don't be shy, okay? We don't bite. Please ask. Normally, Indonesian
Hello,
student
Mas
is
Imam.
really shy. Okay.
Okay. Hello, Longgong. My name is Fauzi, and I'm
Hello?
from ITB. Firstly, thank you very much for delivering this interesting course. I have a question regarding the electrowinning process. My question is, what is the reason? Why did we use rolling aluminum and lead silver alloy plate as the cathode and anode? Is there any specific reason on why we choose these materials as the electrodes? Thank you.
Okay, can you repeat? You mean the electrolyte?
The reason why selecting the certain alloy for the electrode.
Okay, actually, this is a good question. Good question.
Yes, very good question. The reason
very
why,
good question. Yes.
yeah, why select certain type of material for cathode and for electrode.
Yes, actually, this is a very professional question. And first of all, I would like to see the cathode. The cathode used to be zinc, the metallic zinc. So it was started with zinc and terminated with zinc. So we prepare one starter and it grow up in the electric winning process and we sell the cathode. And because this is very low efficient, and we should find how to say a cathode which can fit the large scale production or fit for the automotive production. And alumina is a very good one here because it can resist the corrosion from the electrolyte, especially when we have some 200 gram per liter acid, sulfuric acid. And the alumina oxide layer is very dense. It is conductivity, can conduct, how to say, can transfer the electrons, but it can resist the corrosion. So this is the reason we are using alumina. And the other metals probably they have been tested, but I haven't got the material to know the reason of their failure. But I will assume that in copper electrical refining, we are using some alloy, iron alloy, as a cathode. But here we are using aluminum because I think the steel alloy is not stable here. And for the anode, here we are using the lead and silver. So same reason for this. The lead and silver are stable in this system. And if we are producing oxygen on the anode reactions, and we are using the anodes in acidic conditions, so they should be stable in acidic and sulfate system, and lead should be the first option, and silver is added to increase the conductivity and also to increase the strength of the anode. And the oxidized product of lead and also magnesium, MnO2, and they can deposit on this material, and which can conduct or which can transfer the electrons, and which can also protect the anodes for longer use, like several days, I think. Okay. Have you received my answer?
Hello, Longgong. Thank you very much for the answers. It's very clear.
Yes, very good questions.
Very good question. Yes.
You understand, Fauji? The reasons? Can you repeat? I'm kidding, okay? Okay,
Yes, it-
next question. Next question, guys. We already have good 2 questions. The next one. Don't be shy. Because I also mark the activity of student in the class. The student who very active, asking question, there is also additional mark, you know? Okay, don't be shy.